Welcome back. We're in the Projectiles unit, worksheet 3, the last problem, problem number 7. Let's get into it. So a golfer hits a chip shot. Cool. That's one of the shots with like one of the high number wedges, or maybe a wedge itself, so that you can actually get a nice big arc on it. Launching his ball so that it leaves the ground at an angle of 50 degrees. There's the big arc there above the horizontal. If all goes well, he figures the ball should land the same height 10 meters away. Golfer's attempting to launch the ball over a 6-meter high shrub located 5 meters away. Does he succeed? Well, let's go draw this. Sounds kind of like the Paul Konerko problem from earlier. Let's see if we can draw a golfer. He's got a club there. He's got arms on that club there. Oh, that's not so bad. It looks like a putter, though. He's got a wedge. There we go. That's not so bad. He's having a grand old time because he's outside in the sunshine. Yay! And the ball is what's most important here, so we'll make that a different color. Well, down on the ground. Ball's down on the ground there, goes up at some velocity. Do we know the velocity? No. Goes up at some velocity, and I'm going to go ahead and put in the component vectors there because those are probably going to come in handy. Got some angle there, 50 degrees. We know that this one over here is V naught cosine of 50 degrees. This one's V naught sine 50 degrees. Let's see, there's a 6-meter high shrub. So here's a shrub, and we're assuming the shrub has 0 thickness here. It becomes a little bit harder if it's got some thickness, so I'm going to draw it with 0 thickness, or approximately 0 thickness anyways. So that's 6 meters high. And he's figuring that the ball should land here, which is 10 meters away. So from there to there, and that ball has shrunk in size over the flight here. You hit it so hard that a big chunk of it flew off. We'll make that bigger. Let's see. Oh, the shrub is 5 meters away. Oh, I guess I should move that shrub then, because it looks like it's closer to the end there. So I'll move that shrub. Maybe I'll make the shrub green, because that makes sense. Shrub is 5 meters away. 6 meters high. And 5 meters away. So 5 meters from there to right there. All right. So then the question really is, where is the ball when it's right there? So 2 ways that you can think about that. Number 1, you can think about that as what is the position, when it's at an x position of 5 meters. So what is the y position? And since it's right in the middle, that's probably, well, so it's right in the middle. So the other way to think about that is you go, hey, what's the y max of this? And you know that the y max is going to happen at a x position of 5 meters. And so really that's basically asking the exact same thing, but just recognizing that since this is a symmetric problem here, that it will coincide with the maximum height of this thing. Now, we don't know if it's actually going to get up there or not, but I'm going to sketch something, and I can always go back and change my sketch if I need to. Now, what else do I know at the peak there? Since I recognize it, well, at the peak there, the velocity in the vertical direction at the peak there is 0. Cool, great. I also know that the velocity in the x direction is unchanged from the beginning, which is my V naught cosine of 50 degrees. And it doesn't tell me what the V naught is yet, but maybe I can figure that out. Maybe I don't need to. Who knows? We'll see. So let's go set up our dimensions here, my x dimension calculations, my y dimension calculations. Section that off into 2 columns here, give myself a little bit more space in the y dimension, as I usually need that more. So where is that at the 5 meter mark? How high is it at the 5 meter mark? Well, let's go find the y max. Why not? So delta y is equal to 1/2 at squared plus v naught t. Look at that and go, y max, well, that's going to be from my ending position, which is the y max, minus my original position. Well, you probably said, and maybe you didn't even recognize that you said this, you probably said, wouldn't it make sense to make the ground be 0 down there? And I'd say, yeah, most people do. And so that means that at the beginning there it started at 0, so now we're just left with y max there. Okay, cool. So that's, and I should do that in a different color there. So that's this bit right there. I know the acceleration, don't I? Because anywhere along this flight here, gravity's pulling that thing down, and so then therefore it's accelerating downwards with negative 9.8 meters per second squared. So that's negative 9.8, right? Do I know the time? I don't know the time. Do I know the original velocity? I don't know the original velocity. It's v naught sine of 50 degrees. And then I see that here I can't solve this straight away because I don't know y max. I don't know the time, nor do I know v naught. So I actually have 3 variables I don't know. So I'm a little bit stuck here. So I'm going to do a couple things. One, I'm going to scroll down here a little bit, work in the y dimension a little bit more, and I'll say, hey, I know that v is equal to at plus v naught. Maybe I can do something with that. Let's look. Well, the velocity, remember this is at the peak, so the vertical velocity I know is 0. The acceleration is going to be negative 9.8. I don't know the time, that's okay. And the vertical velocity, well, I don't really know it, but I know that it's v naught times the sine of 50 degrees. Okay. So now here I have 2 unknowns, and so well, it gives me another equation, and so that can be helpful. Let's go rewrite this. So I have 0 is equal to at, well, I'll put in the values here. 0 is equal to negative 9.8 t plus v naught sine of 50 degrees. And now I could solve for either t or v naught. But notice I still wouldn't be able to solve this because I have 2 variables here, which is fine. And then over here, I have 2 variables as well. Actually, I have 3. Let's look at those. Starting from the left, I don't know y max. Great. I don't know t. And I don't know this v naught there. So, man, I need another equation. Well, I'm kind of running out of ideas here in the vertical dimension, so let's go over to the x dimension. I know that delta x is 1/2 at squared plus v naught t. And I also know that the acceleration in the horizontal dimension is 0. Nothing's pulling or pushing it that way. And so I have delta x is equal to, now the original velocity in the x dimension is v naught cosine of 50 degrees multiplied by some time there. Okay, great. So now do I know anything? Let's go up and see if it gives me any given values, any initial conditions here. And it says that it should land 10 meters away. Okay, so whatever speed they hit it at, it should land 10 meters away, meaning that 10 meters should be equal to v naught cosine of 50 degrees times multiplied by that time. Now, this equation, this teal equation, could help me with this black equation down here to actually eliminate one of these variables. Let me be specific here. In the right-hand one, this is the time to the peak there. Now, since this is a symmetric problem, we look over here, right? This parabola is nice and symmetric. The total time t is going to be twice that of the time to the peak there. So this t is going to be 2 of the time to the peak, right? It's just cut in half because it's a nice symmetric problem there. So I'm going to go ahead and I'm going to put that in. I know that that time is equal to 2 of the times to the peak. And now I'll have the same variable there. So let me go rewrite that. 10 is equal to v naught cosine of 50 degrees times 2 of my times to the peak there. Now that can be helpful because now look at this teal equation, I have 2 variables, and the black equation down here, I have the same 2 variables. So I can eliminate one of these, and if I can eliminate one of those, then I can be able to actually solve that this equation right up here in the y dimension there. Okay, so let's go see if we can do that. Well, what do we care about? Well, we care about the v max. We don't care about any of this other stuff here. So let's go. So it doesn't really matter what we solved for.
So I'm going to go ahead and I'm going to solve for the time to the peak, because why not? We'll get both of them anyways. So I'm going to move everything over to the other side. So I have 10 over V naught cosine of 50 degrees, and then I divide by the 2 there as well, and now that's equal to the time to the peak. And I could put that straight in for there and then clean all of that up. Now that'll actually get messy. I'm looking at this and going, hey, I could plug that in there. But I think that's going to get a little bit messy. I got to multiply, I got to get common denominators, and that's looking a little bit messy there. So I'm going, okay, well, I could have easily just done it the other way and solved for V naught. Maybe that'll be nicer algebra there, and sometimes it is. Divide by 2TP, and then divide by the cosine of 50 degrees, and that's equal to V naught. Now I'm thinking about this and going, hey, what if I put that in there? How's that going to go? But that looks like it's going to go a little bit better. Sine and cosine, that gives me tangent, and I can clean this up a little bit. Either way, you'll get the exact same answer. So let's go do it this way, though. Sometimes it's like way easier one way, and other times it's, not. So it's always good form to at least look at that and think about that. Might save you a little bit of time. So that's 5 times the sine of 50 degrees over TP times the cosine of 50 degrees. Okay, cool. So then I can just clean that up a little bit. Sine over cosine just gives me the tangent of 50 degrees. And then TP here. So how do I want to solve that? Yeah, so I'm going to subtract that over to the other side. So I'm going to do -5. Oh, I got to give myself some more room. -5 tangent of 50 degrees over TP is equal to -9.8 TP. Multiply by TP on both sides, divide by the -9.8, and so now I have TP squared is equal to -5 tangent 50 degrees divided by -9.8, and I take the square root of both sides to get me to TP by itself. Great. Hey, that wasn't too bad. Got to give a little bit of thought. The negative and negative, -5 and -9.8 is good, because then it's going to give me some positive value when I go to take the square root of that, which I expect to have, and I'd have a problem if I didn't have it. So 5 times the tangent of 50, I'm just grabbing my calculator now, divided by 9.8, and I make sure to take the square root of that. And I find the time to the peak to be 0.78 seconds. Now I go and store that in my calculator as the whole string of numbers there, of values. 0.78 seconds. Now, how does that help me? Well, I actually need to go and find out the V naught there as well. So I'm going to go take this, and I'm going to plug it back into that guy right there so I can figure out what V naught is. So let's go do that real quick. And then we've solved for 2 variables, which is nice. So V naught now is, we have 5 over 0.78. Remember, the whole string of values times the cosine of 50 degrees. So I find that V naught is, we have my calculator, 5 divided by, don't forget parentheses, my time there, which I stored as t, times the cosine of 50 degrees. And I get V naught to be 9.98 meters per second. Oh, that's nice. I'm going to go store that because I bet that'll be useful. I'm going to store that as V so I don't forget what that is. And so that is the original velocity. That is actually V naught there. Great. So then I look back over here and go, hey, now can I solve, let me highlight this, now can I solve this equation right here? Before I couldn't because I had 3 variables, V max, T, and my my V naught. Now this was V, so this is Y max here. This is actually TP, the time to the peak there. So now I can go and solve that because I know the time to the peak, I know the original velocity, so I only have 1 variable there. Okay, great. I'm going to get rid of this red stuff there though, and make sure to put the TP back in there.
So now I can just solve this. So I got y max is equal to 1/2 negative 9.8. My time to the peak was 0.78. And remember, I'm using the whole string of values there. Plus my V naught was the 9.98. And then sine of 50 degrees multiplied by my time value, which is 0.78. Oops, that gets in the way. And don't forget the decimal place. I gotta get it. There we go. And so then we just throw that in the calculator there. Good thing we saved all of those values. So then I do 0.5 times negative 9.8, my time, and I can square that, plus my v that I stored for velocity, and then times the sine of 50, multiplied by my t. And I get 2.98 meters for a y max there. And I go and compare that to what I had for the bush. The bush was 6 meters high, so here it doesn't even make half of that. It just makes less than half of that. This is the actual. So no. We go, no, he does not succeed. We do 6 minus the 2.98, and we get 3.02, and we go 3.02 meters short of clearing the bush. It didn't actually specifically ask for that, but it'd be an interesting thing nonetheless. Maybe he needs to change the angle that he shoots that at. Really, he just needs to change. Well, he could change the angle if he got closer to it. But it's golf, and it doesn't work that way because he can't kick the ball. So that's it. A little bit more of a challenging one, but not too bad. We can still do it. All right. Take care. See ya. Have a beautiful day. Bye.